We next discuss matrix-matrix multiplication, and this is possibly my favorite operation. I can actually take a lot of issues in high-performance computing and linear algebra and boil it down to illustrating the issues with this operation, which is much simpler. And I jokingly say that I may just go down in history as having written the most papers on matrix-matrix multiply of any researcher out there. We'll see how long that holds up. Anyway, what's this operation? Okay, you have a matrix C and you compute it as A times B. And if C is an M by N matrix, then A is an M by K matrix and B is a K by N matrix. The important thing being that this row size of C must match the row size of A, the column size of C must match the column size of B, and the column size of A must match the row size of B. And as before, we like to often go and add C to it, and actually the most general case of this is where you then multiply A and B by a scalar alpha and C by a scalar beta, but let's not get into that. So let's look at how C is actually computed. I noticed that we are adding C to the result, and we might put a colon equal here. Let's think of B as being two columns. In general, of course, you would have more columns. And let's think of C as having two columns. So the bar here separates the left column from the right column. In general, bars would separate the different columns. If you now look at a typical element in C, how is that computed? It's computed as the dot product of the corresponding row in A with the corresponding column in B. Okay, and if you think about all elements in that column, then what do? Well, you do dot products like that, of course adding to the elements of C. But what operation is it when you do this dot product followed by this product followed by that product? Oh, that's just a matrix vector multiply. Okay, so if we generalize this, what do we get? We leave A alone. We think of B as a bunch of columns, N of them. We think of C as a bunch of columns. We're adding it to the original contents of C. Let's see, because we're doing an assignment, we don't need to put hats on there. And what do we conclude? We conclude that the jth column of C, for every j from 0 to n minus 1, can be computed as A times the corresponding column of B added to that column of C. Okay? All right, now, that does not give us a partitioned matrix expression. So let's see if we can take these insights and work it into a partitioned matrix expression. Well, think of a left part of the matrix, let's call it CL, and a right part of the matrix, let's call it CR. And let's think of doing the same thing for B. And of course the original part of C, the original contents of C, like that. What do you notice? Each column in the left part is simply computed as A times the corresponding columns in the left part added to the columns in the left part. So we can conclude from that that the left part of C should be updated as A times the left part of B plus the left part of C. And similarly, you can see that, let's give ourselves a little bit of room. Similarly, we can see that the right part of C should be computed as A times the right part of B plus the right part of C. Okay. Okay, let's massage that a little bit further. That's just equal to A times the left part of B plus the left part of C on the left, and A times the right part of B plus the right part of C on the right. So when we're all done, what should be in C? A times the left part of B plus the original contents of C. And what should be in C right? A times the right part of B plus the original contents of C right. And there we have our partitioned matrix expression. And once we have a partitioned matrix expression, we can say, what are the loop invariants? And once we have the loop invariants, we can derive algorithms. Okay, so why don't you go ahead and derive some algorithms for this particular case.